Welcome to Sigma Solver guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to look at another topic which is related to Euler's method and its application in modeling and simulation. So let's read the question first. Explain the working principle of Euler's method. Also discuss the disadvantages of Euler's method. Write down the general numerical scheme of Euler's method. Using this, with step size h equal 0.1 and we need to find y of 0.2 for this given differential equation. dy by dt equals y square plus t and y of 0 equals y naught, which is equal to 1. So first we understand the working principle. In that, Euler's method is a numerical technique used to approximate solutions to ordinary differential equations when a data driven analytical solution is difficult or impossible to obtain. This is when we have a particular given problem and the analytics that we get from, let's say, Power BI or MS Excel is not quite getting inserted properly into a known statistical scheme, right, which is theoretically established. Then we try to approximate the solution of that particular model which we are trying to build using ordinary differential equations. And the simulations that we do in this process is what we will be discussing under Euler's method. It provides an iterative approach to finding the approximate values of y at discrete points. So as mentioned previously, that in those cases, let's say this is the graph and there are spikes and again there is curve, right. So at places we don't know whether the curve is going to stay differentiable or whether it's not, right. So what we try to do is we try to iterate the approach, let's say for this particular zone, y plus 1, y plus 2, like this, and we try to approximate the values of y at a given discrete point. So now let's understand the principle behind Euler's method. So it works on tangent line approximation to estimate the next point based on the slope at the current point, right. It is similar to what we have as the base principle of differentiation. The only difference is we are trying to deal in a scenario where there might be multiple functions leading to a composite function which we are trying to analyze, right, and that approximation is more likely to follow a tangent line approximation which will give us results that are near to the actual value. So given the first order ordinary differential equation is dy by dt equals f of t comma y. Now with an initial condition of y t naught equal to y naught, which was given in the question, the method goes as below. We need to start at the initial point, which is t naught comma y naught. Then we need to compute the slope of f t naught comma y naught given by the differential equation. Third, we need to use the slope to estimate the next value using the below formula. Yn plus 1 equals yn plus h times f of tn comma yn. Now notice that we are using tn or nth time and not n plus 1, because that is what we are going to estimate, right. This is what we will have based on the previous step and we will go in an iterative fashion. Now we understand what these terms mean one by one. H is the step size, the interval between the successive points. So let's say there are 10 points in total that we want to approximate. So h is going to be the step size that is marking the distance between two consecutive points. F tn comma yn is the derivative at tn yn. Yn is the current value of y. Then yn plus 1 is the estimated value at the next step. Now when we go to the next step, yn plus 1 becomes the current value at that particular time. We need to repeat this process for subsequent steps until the desired value of t is reached. So let's say we want t10 and we are at t5. So we need to go approximate one by one up till t9, and then t9 will eventually give us value of y at t10. Therefore, Euler's method essentially approximates the solution step by step, moving forward in small increments. Now we come to the disadvantages of Euler's method. First is low accuracy, of course. Since Euler's method is a straight line approximation, error accumulates at each step. Just like linear regression, similar approach is followed here as well. As we know, in linear regression we have MSE, and it basically sums up the square of errors occurring at different points the line passes through and adds them all, right? But in the case when the curve is a bit different, or I'll say has curvature to it, and the line that we are estimating is around this thing, so adding the errors from this line to the actual line won't make much sense, because it will perfectly align with the expected or actual behavior in this point, but beyond this point we will need a completely different line to estimate that. Similar is the case with Euler's method. Since it is again using a straight line approximation, so moving from here to like down below, error will accumulate over time, causing unrealistic error values. Next, the method has a global error of order O of h, meaning the error is proportional to the step size. It is very clear that if we reduce the step size, then the behavior of the function will get more described by the small line segments that we draw at each step, and therefore Euler's method may prove to be a better solution. But as we know that if we reduce h, it will exponentially increase the number of steps that we will need to reach to the point t destination, right? And this will ultimately increase computation time, which might not be desired in your application. Then we have instability for large step sizes. So if the step size is too large, the method can produce oscillations or diverging solutions instead of following a correct path. So now for oscillations, let's dig into an example. So we'll consider a very basic example here, which is dy by dt equal to minus 10y and y of 0, let's say, equals 1, right? So analytical solution for this one is yt equals e raised to power minus 10t, right? As we can see that it is going to decay smoothly towards 0 as t increases. But if we now apply Euler's update rule, we'll get y of n plus 1 equals yn plus h of minus 10 yn, which boils down to yn times 1 minus 10h. Now, if suppose we choose h to be 0.2, which is large in this context, then yn plus 1 is going to become yn 1 minus 2, right, which is minus yn. Now, if we look at it from a numerical standpoint, y1 equals 1, y2 equals minus 1, y3 equals 1 again, like, and so on, right? We are not estimating this properly, right? That is where the error with oscillations due to a large step size is occurring, as resulting into an oscillatory behavior. Okay. Next, let's think of an example where divergence is also demonstrated. So we consider, let's say, dy by dt equals y and y0 equals 1, right? So analytical solution again in this case will be yt equals e raised to power t, right? Now it is very clear that this is exponential smooth growth, right? And if we try to put this now into Euler equation, it's yn plus 1 equals yn plus h of yn, right? If we take this out, yn 1 plus h, right? Now if suppose we chose again a very large h, let's say h equals 1, then it's yn plus 1 equals 2 times yn, right, which will again cause a divergence behavior, which you can see from here is y1 2, then 4 8 16 and so on, right? which is again not estimating this properly, and I have taken it for E, and 2 is accordingly quite near to it, but for other equations where it is, let's say, alpha raised to power t, it may vary completely different, right? Or if, let's say, I put h equals to 2, right? So in those areas the Euler method may diverge completely different from the actual behavior. Alright. Next we come to poor handling of stiff equations. So for equations where the solution changes rapidly in some regions but slowly in others, Euler method struggles because it requires extremely small step sizes to remain stable, right? As mentioned previously, that a curve like this, right, which is more likely to be of an impulse, is going to change rapidly in some regions but not in others. Now Euler method will completely ignore this if the step size is large enough, right? So the size of the spike or the trough may not be known in advance, so Euler method may struggle here as well. Next, it requires small step sizes for precision. To reduce error, a small step size is needed, of course, which increases number of iterations and the computational effort. Another important consideration is it is limited to first order equations as well. Therefore, we can say that Euler's method cannot be applied for something like this. Basically a polynomial of the differential equation, right? So we just can't apply Euler's method, at least in this format, for differential equations of higher order than 1. Now we solve the given equation, which is having the initial value of the problem as dy by dt equals y square plus t, where y0 equals 1. With step size 0.1, we need to approximate y of 0.2. So we compute y of 0.1 using Euler formula. y1 equals y0 plus h times of f of t0 comma y0. Substituting the values, we simply can get 1.1, but essentially if we look at it, it's equal to 0.1, right? Y of 0.1 was equal to 1.1. Now we compute y of 0.2, but here we'll use this particular value. Using Euler formula, again we get y2 equals y1 plus h times the function itself. We substitute the values. Now if you see here that since we are squaring it, which is y1, and it is again an approximated value, so error keeps getting added like this behind the scenes. So that is what is written here, right? So in that instance we just multiply it in the same manner and we get 1.231, right, which is equivalent to the value of y 0.2. Now this was one method of approximation. Again, this is not the only method that we can use to approximate complex functions of composite behavior. There are other methods like Runge-Kutta methods and adaptive step size techniques, right? This is a completely different method, while adaptive step size technique can be applied to a modified Euler method to tackle edge cases. So that's how you use Euler method to approximate a given differential equation. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.